So let's start. So we're here to show you quantum machine learning in action. And the reason is because we strongly believe that quantum is an essential part of making machine learning better. Okay? And this is true both in the future, when we will have better hardware, better quantum hardware to run actually quantum algorithms in this hardware, but also today by taking quantum ideas and turning them into classical machine learning solutions. Okay? So we'll see how to do that through QClearn. So what is QClearn? QClearn is a cloud-based software solution for data scientists and quantum developers. Okay? It extends widely used machine learning libraries, things like sklearn, PyTorch, TensorFlow, JAX, things that any data scientist uses. So it extends these libraries with new quantum and quantum-inspired functionalities. And it runs both today on CPUs, GPUs, and TPUs, and it also on available quantum hardware, for example, IonQ or Rigetti through Bracket or IBM Q. What QClearn does is that it turns quantum ideas into powerful machine learning tools. These ideas can come from geometry, topology, other domains from mathematics, and we turn these quantum ideas into machine learning tools that first lead to better models today, since as we said, we can train these models today on classical hardware, on GPUs and TPUs, and are also QPU compatible today, meaning that we can start testing these algorithms on the available quantum hardware and be ready from now for the next generation of quantum computers where we can actually do something more interesting. So QClearn can be used for quantum proof of concept projects. We can try to understand what is the potential of quantum in machine learning. It can also be used for data science explorations where we can benchmark classical models against quantum and quantum-inspired models. But more interestingly, it can also be used in machine learning workflows in production today. As we said, any time that a data scientist uses sklearn or PyTorch within a machine learning pipeline, we can just substitute specific functionalities with our own functionalities, keep the pipeline the same, and start seeing today improved models. Okay? So before we see QClearn in action, let's try to get a peek under the hood, where we'll see a little bit what are the mathematical tools on which QClearn is built on. So the first one is determinantal sampling. So determinantal sampling is the mathematically optimal way of ensuring diversity in the data while training. And this makes the models more robust and more generalizable. We have our orthogonal and geometric neural networks that train features which are independent and disjoint, hence maximizing the expressivity and the interpretability of the models. We have subspace learning, which is a series of techniques in learning which are specifically designed for dynamic data sets. For example, data sets that have to do with time series in finance or with trajectories, multimedia, video, etc. We also have compound kernels and also topological learning that use geometry and topology as a way to enhance features and capture important global properties of the dataset that otherwise go unnoticed. And last, we have manifold optimization. This is a way of generalizing the optimization landscape that tries to encapsulate much more complex datasets and provides more meaningful and accurate models. Okay? All of these methods here, they come from deep mathematical areas that can lead to better models, as I said, today when we run these algorithms on GPUs and TPUs. And at the same time, they are native for quantum computers, meaning that we expect that quantum computers in the future that run this algorithm will actually be even better and provide even better models than what we can do today. So without further ado, let's see how we run QClearn in practice.
Thanks, Iordanis. Quantum software should be easy. So instead of designing a brand new library that you would have to learn, we've designed a series of extensions to popular machine learning libraries. So here is how a data scientist might import these libraries today. And forget a one-line change. This is a one-word change where now you can start using the QC-learn versions of these models. So for TensorFlow, for Torch, for JAX, and for scikit-learn. Now, the core of QC-learn is that it blends quantum and classical data science. And the way it does this is this one very special method called set backend. This is a master control that allows you to select which version of the algorithm that you want to run. And your choice matters a lot. So you can run this on quantum backends. We support natively all of the cloud-based, gate-based quantum computers of today. So we're native on Amazon Bracket, and we have support for IBM. But the quantum computers of today typically can't run the data sets of today, so we also have a set of simulators. And these are new simulators that are designed to be compatible with the libraries that they're extending. For example, if you have a JAX workflow and you use the JAX simulator, now the simulator itself can be compiled in with JAX to get optimal performance on GPUs and TPUs, and also has those great benefits of differentiability. And of course, we also run on Bracket simulators and Qiskit simulator. But the big point about QC-learn is that it has a third option, which is classical. Now, we've designed these classical algorithms to take these quantum ideas and turn them into tools that we can use to get benefits today in machine learning pipelines. By default, QC-learn automatically chooses the fastest way to run your algorithm. That means typically, or all the time today, it's using classical. But as the quantum computers get better, it'll naturally switch to quantum. So we can see this in action. If you want to build a prediction model, you might typically import a random forest classifier from sklearn. Now, if you want to use an enhanced random forest, which is enhanced by determinant sampling, which is an algorithm in QC-learn, it takes one change to the import and then one change to the initialization, and you're off. So when we make this change, we find a broad variety of fields can find improvement. For example, in diabetes prediction, in churn prediction, and in synthetic data sets like the Madelon dataset. And by default, we are using the fastest way to run the algorithm, which is the classical algorithm right now. And when we benchmark against open source solutions, we find that as the problem size gets larger, we do orders of magnitude faster. And so this is really performant custom code. If you want to run on a quantum computer, it's just one line, set backend, to say bracket/IonQ. And once you do this, you're automatically outsourcing those very computationally intensive portions of this algorithm to a quantum computer. Now, neural networks work the same way. For Torch, for example, a data scientist might define an architecture like this. And to use some of those advanced neural network layers from QC-learn, it takes a few changes to the import, and then a few changes to the architecture itself, and you're off. So likewise, we find that when we make the switch, we can find improvements in a wide variety of fields, for example, these CT scan data sets, manufacturing data sets, and some benchmark data sets like Retina MNIST. And Iordanis will also talk about some of the projects that we've been doing with industry. Now, one thing that I want to note here is that if you're using the Torch simulator, now it's built into the Torch pipeline. And because we can design custom simulators for the algorithms, we can now simulate up to 60 qubits or more. And of course, if you want to run on hardware, for example, IBM /Hanoi, we can do that with one line. And with that, I'll pass it back to you.
Yeah, so thank you, Sohum. We saw some ways of using QC-learn, and now I want to show you some real-world use cases on where we have used actually tools which are now on QC-learn and see how we did over there. So this is the first example where it was a collaboration between QCware and Itaú Unibanco, the largest bank in Latin America. And the goal of the project was the following. We wanted to predict which ones of the premium customers of the bank is likely to leave the bank in the next few months based on their past financial transactions. Okay? And we started with a benchmark which was the model that was used in the bank at the moment, which was a random forest. And by using the QClearn functionalities of adding determinant sampling on top of this random forest, we managed to improve by 7% the accuracy of the model, which, according to Itau, it corresponded to more than 40 million US dollars more money captured per year by the model than by the previous model. Here is another example. This is a collaboration with a top pharmaceutical company, where here we wanted to use patients' data from clinical trials in order to predict their survival rate. Okay? The main problem here is that a lot of this data is actually missing. So what the machine learning model has to do is first complete this data and then use it in order to predict accurately the survival rate of the patients. Okay? So again, by using techniques that come from determinant sampling, we managed not only to increase the precision of the prediction, but more importantly, to find a way to complete this data in a way which was consistent and reproducible. And this was actually the main goal of the project in order to be able to actually use this in practice and through regulatory conditions. Okay? Here are some more examples that have to do with neural networks. These are cases where we used our orthogonal and geometric layers within neural network architectures. We did it with BMW Group to design convolution neural networks for quality assessment. We used it with Roche to construct vision transformers, and we used it for diagnostics, for using medical image classification. And in an ongoing project with one of the top 3 investment banks, we used our neural network techniques within the framework of deep reinforcement learning for the use case of hedging. In all of these use cases, what we found is that using our neural network techniques can give at times more expressive models, meaning models with much fewer parameters, better accuracy, and very fast training, meaning that we can actually train scaled-up architectures with real-world data sets. There are many more use cases, right, where we can use the same techniques. Generally, in predictive analytics, object classification, customer value prediction, and recommendations. In particular, in life sciences, we can use these techniques in drug discovery and drug development cycle for clinical trials and for diagnostics. And also in finance, for analysis of time series data like stock prices, for fraud detection, and for risk assessment. From all of these use cases, I want to just highlight one of them, where we will see that what we did in QClearn is not only to enhance and improve methods which are already out there in the classical machine learning literature and libraries, but also design our own ways of classifying that actually can improve very significantly the accuracy. So we will look at object classification, and I'll let Sohum take it from here.
Thanks. So QClearn includes a new type of model, which is called the subspace classifier. Now, this is an idea from quantum computing, but we can do this entirely classically. The subspaces are a powerful mathematical tool, and they're very powerful for data sets that are dynamic, like videos and trajectories. And here we'll see an illumination data set. So here we have 2 images. Both of these are of the same cell, but they're illuminated from different sides. And normally, in a data science pipeline, you might take both of these cells to be individual data points. But in this new method, we find that we treat these data points in a joint representation called a subspace. So these are individual data points, but instead we're treating them like a subspace. And we can benchmark this simple change against some of the typical similarity-based classifiers that we find today. And we do find that the QClearn subspace classifier does significantly better, up to 10 percentage points. So this is an example of a quantum idea. A quantum computer can, in fact, do much more complex operations on subspaces, but the classical methods that we have today can actually take us a long way in improving our models. That's it.
When we say we are doing better, we have the numbers to back it up as well. So let's go to the summary. So I just wanted to conclude. So what we did is that we tried to present QClearn, right, which is a quantum-powered machine learning engine that offers ease of use and compatibility for data scientists. We want to give the possibility to data scientists to use quantum computing the same way they're using classical machine learning. We have fast GPU-based methods for better models today. We saw some examples. We have many more. And we also offer optimized quantum algorithms for benchmarking today. So please come and find us at the QCW booth. We can show you many more, also live demos on different data sets, running on GPUs, running on quantum simulators, running on quantum hardware without you having to change anything. And I just want to leave you by saying again that we strongly believe that quantum is key to better machine learning. As I said, both in the future, when we will be able to run quantum algorithms on the next generation of quantum computers, right? And we can provably enhance the capabilities of machine learning. And also today, by taking these quantum ideas and turning them into powerful classical machine learning solutions, as we did with QClearn. So thank you very much.
Okay, we have time for a couple of questions. Yes. Hi, thank you so much for the talk. Oh, right, that's okay. So you showed an example where you had some improvement in the versions that are the quantum algorithms, that in the AUC, the area under the curve, was a bit better. Is that's a classical algorithm? Well, it was run on a classical system, right? It wasn't, yeah. So, does the improvement come from the fact that this was like a better algorithm that was quantum inspired?
Or the regression that one uses from sklearn, for example, like the random forest classifier, to our own version, which is called the DPP random forest classifier, that uses these techniques of determinant sampling within the random forest classifier. So this is a new algorithm which today runs on GPUs, and we know that tomorrow in the quantum hardware can run actually even faster and give you even better results. But the results that we saw in the improvements you can actually get today by running a better algorithm on GPUs.
Thank you, thank you, thank you.
Hello, thank you for the clear demo. I just wanted to know if this is available right now and if it's open sourced or if there's a price model that you've set already.
Very good question. So QClearn is available to our customers through our proof of concept projects right now, and it will be available on the cloud marketplace. So the moment you will see a quantum cloud marketplace happening, then we will be there, and we should be happening sometime in 2023.